Okay, hello. So today we'll be looking at this function you can see there and on your screen. So let's quickly just go through the info provided. They gave us two functions. One is this exponential graph at the top, which is f, and then the other one is a hyperbola, which is the g1 at the bottom. Then they said y and a and d are y-intercepts and f is an x-intercept, and then fx intercepts the vertical asymptote of gx at c, which is that c point there. And then f is a x-intercept, yes. So, and these are the two functions provided. The one is exponential, the other one hyperbolic. So let's look at the questions then. So in the first question, they asked us, I'm going to read it now. Let me just mark it 2.1. So they said fx can also be written as, let me write it down. So they say fx can also be written as 2 to the power of x plus p plus 6. Sorry. So all we need to do is let's write down the one that was provided to us. It's 1 over 4 times 2 to the power of x plus 6. Now what we're going to do is we're going to adjust this one to get it in the format that we wanted. So we can write this as 2 to the power of minus 2, which is the 1 over 4, times 2 to the power of x plus 6. Then if the bases are the same, I can add the exponents as here. And now I have it in that form. So now I can easily pinpoint what p is. So p should then be this value here, this one there. Okay, so all I'm going to do is I'm going to say thus p equals minus 2. Right, so by simple algebraic manipulation, we could isolate the p and show what it was. Next up, let's look at 2.2. So in 2.2 they said, give the equation of the axis of symmetry of gx with a positive exponent. Now if we use the standard form, let me just write it down, we'll have either a plus or a negative gradient. X, it's a gradient of 1, which we'll be using here. So just to remind you, the axis of symmetries go through here, just to maybe show them to you. So you have two axes of symmetry, one negative, one positive. And both of them will pass through this, which was in its standard form is the origin, but now it shifted. So basically, I do have a standard line. We wrote it down there. We said it's y equals plus or minus x plus c. Since we're going to be using the positive gradient, we'll say y equals x plus c. So I need to calculate that c, but I can only do it by having an x and y coordinate. So I need a vector, vector components, and so I need to know what does this line pass through. And for that, I need to understand the asymptotes of the hyperbola. So if we look at the standard format for a hyperbola, maybe we can... So the standard form for a hyperbola, just to remind you here, let's quickly draw a simple graph. The standard form is like this, okay, and then you get also in the other quadrants. So usually then the asymptotes is the x and the y axis, and your axis of symmetries will pass through that origin. But now my hyperbola, the hyperbola given here, is different because they translated it by adding 6 to the function, and they also subtracted 4 from x. That means they shifted the function to the right by 4 places, and they shifted upwards by 6 by adding 6. So my new asymptote will be the coordinate 4 and 6. That will be my coordinates, and that's also the point through which the line, that's the point through which the line goes. So I can then substitute that coordinate for my line by saying y is equals to 6 there, and x is equals to 4. And I'm using the positive gradient, so we'll just substitute 4 there. And now c can be calculated by algebraic manipulation as 2. So the axis of symmetry will be y equals x plus 2. Okay, that's fairly simple. Let's go to 2.3. So 2.3, they asked us, determine the length of AD. So the length of AD, to remind you where AD sits, so AD, D is the y-intercept of the G function, and A is the y-intercept of the F function. So basically, if I want to calculate YD, I need to know where does if I want to calculate the distance of AD, I need to understand where does A intercept the y-axis and where does D intercept the y-axis. So I need the y-intercepts basically of the two functions. That's basically what I need. Then I can subtract D from A and then get the distance of AD. So that's fairly simple to do. And that's because I know that on the y-axis, the x will be 0. So I can use both functions. So I can take the function of f. Okay, let's write it down. It's we got the standard form as x minus 2 plus 6 in one of the previous questions. And then g, just to write down the equations again, is 1 over x minus 4 plus 6. Right. So that's the two functions. What I need to do is I need to know what is their y-intercept. So let's calculate the y-intercept for the f function. That's where x equals 0. And that becomes then 1 over 4, which, because it's 2 to the power of minus 2, plus 6. If I calculate that, that's basically 6 and a quarter. But maybe we want it in a fraction that makes sense. So I need to get the denominators the same. And so I'll end up with 25 over 4 if you calculate that. So that's the y-intercept for the f function. For the g function, I need to do the same now. So the y-intercept for the g function, also where x equals 0, will be 1 over x minus 4 plus 6. And so I'll end up with a minus quarter plus 6. Okay, so you can already basically see what this distance will be, but let's continue with it. But it starts to make sense what the distance is supposed to be. So then I'm gonna, if I calculate this one, I'll end up with, it's gonna be 23 over 4. That's this distance. So if I need to calculate the distance, so I have now this one, remember, this y-intercept is the point of A. So this here is A, and then my y-intercept for D is this point. So this is D, right? So if I want to calculate the distance of AD, let's write it like this. So if I want to calculate the distance, let's call it distance of AD, then I'll need to take A, which is, as we saw, is 25 over 4. And I need to subtract the y-intercept of D, which is 23 over 4. And then I'll get it's 2 over 4, and I can simplify it to a half. So the distance between the 2 points is a half. Right. Next one. In the next question, they asked, so this is now 2.4, I believe. They say determine the coordinates of f. So let's quickly just remind ourselves what f is. So if we look at f here at the top, so f is the x-intercept of the g function. Now, I mean, if x equals, if we need the x-intercept, it's fairly simple. All we need to do is we have to substitute for y equals 0, right? So if I write my function again, just to have it here, it's 1 over x minus 4 plus 6. What I need to do is I need to substitute for y equals 0 because it's the x-intercept. So I'm going to substitute y equals 0, and then I can calculate for x because now I only have one variable. By using algebraic manipulation, I'll end up with something like this. So it will be, I need to multiply by x minus 4 everywhere. That's the common, that will be the common denominator, but I can multiply basically on both sides, right? So I'm going to multiply this side by x minus 4, and I'm going to multiply this side by x minus 4. So that I can get rid of the denominator here, right? So if I do that, then I'll end up with a function that says 0 equals 1 plus 6x minus 24, right? So now through manipulation, I'll get, I'm going to, through manipulation, I'll end up with x equals 23 over 6. So that will be my x-intercept, which is f for, and all I did was I made y0 multiplied by the common denominator and then simplified by algebraic manipulation and got x. Yeah, by doing that. 2.5 then. So 2.5, they say determine the coordinates of C. Now, if you remember correctly, C is the place where the f function basically intercepts the asymptote, the x asymptote of g. Now, we know that for the g function, the x asymptote will be x equals 4. So basically what I need to do is to calculate the coordinates through which, sorry, no, not the g function. We're working with the x function, yeah? So the f function, which I'll just quickly write down again, is 2 to the power of x minus 2 plus 6. And what I need to do is I need to get that c coordinates. Now I know that what's the x coordinates of c, and that's 4, because it intercepts the asymptote of the g function, and the asymptote of the g function is 4. So I know the coordinates of c. C's coordinates is 4 and y. The y is the one I want. So all I'm going to do is I'm going to substitute for 4. Okay. All right, let's just scroll down a bit here. So then I'll say y equals 4 minus 2 is 2 to the power of 2, which gives me 4 plus 6, so I have 10. So then I know that the coordinates will be 4 and 10. Okay, easily enough. 2.6 is the next one. They say give the equation of hx if hx is the graph of gx reflected in the y-axis. So basically what they're saying, because if you reflect something in the y-axis, let's do a quick test here. So if I have a graph, any graph, in this case it's a hyperbola that goes like this. So if I have a graph and I reflect it over the x-axis, what will happen? It will swap around, right? So this part will swap to that, and then this part will basically, so I can basically swap it around or reflect it. And then what will happen is, it's over the y-axis, excuse me. No, I'm reflecting over the x-axis now. They asked, what if I reflect over the y-axis? So if I reflect over the y-axis, then this part will swap to that side and that part will swap to the other side. But then I have to switch signs for the x, okay? So basically that's by saying hx, which is the graph they're asking for now, is equal to g minus x. So I need to change the sign of x because I'm reflecting over the y-axis. If I reflect something over the y-axis, then its reflection, so you should see the y-axis as a mirror almost, and the reflection will turn around. It's the same as when you look in a mirror. And in the mirror, your right hand will be left, and your left hand will be your right hand, if you look at the picture. And that's basically what happens. It turns around. So if I reflect over the y-axis, then I need to change the signs for my x because it reflects over that axis. So basically, the graph swaps over this axis like this. So it swaps over that axis. So I need to change around the sign of g. So basically, hx is then just saying hx is simply just a graph of gx, but I need to change the sign, sorry, that was a 4, of x. Now I can simplify it by taking out minus as a common factor in the denominator. And once I do that, then I'll end up with this. Let me maybe repeat the steps. So then it will be x plus 4. And then obviously 1 divided by a negative is a negative 1. So I can write this function as minus 1 over x plus 4 plus 6. So now you can see that basically the way it works is after the reflection, the asymptote for x now is not 4, but minus 4. So that basically the graph swapped its places. So where usually it went down the asymptote of x equals 4, now it will go down the asymptote of x equals minus 4, whereas the asymptote of 6 stays the same. So the reflected graph to show you what the reflected graph will look like is it will now pass through this point here and it will go down here. So it's just a reflection. It's just a reflection of the y-axis. That's what happens here. So now my asymptote will be here, which is the -4. And that's basically what happens. So I just swapped the sign of x. And now the last question, 2.7, they asked if the points m, so they say m, let's write down m they say is 1 and y, and the point n, so there's another point they gave us, and this point is x and 7, they say lie on fx. So both these points lie on the graph of fx. Determine the average gradient between m and n. Now, I mean, the average gradient, if you remember, let's call it the average gradient of m and n. We usually will write it as this. We have two x coordinates and two y coordinates. So basically we can write it as, let's say it's the y coordinate of m minus the y coordinate of n, divided by the x coordinate of m minus the x coordinate, sorry, that should be capital, the x coordinate of n. That's what we need if we want to calculate the gradient. So what I'll need is, because I do have the x coordinate for n and I have the y coordinate for n, I need the y, so I need this y and I need that x. But that I can do by substituting, because I do have a function that defines these points. I have this function. They said it goes through this function, fx. So it goes through this function. It's 2 to the power of x minus 2 plus 6. So what I'm going to do is to get the y coordinate, this one, of m, I'm going to substitute the x coordinate of m. So basically, the y coordinate of m is 2 to the power of 1. Sorry, I need to substitute 1. Let me substitute 1 for x. So I'm going to substitute 1 minus 2 plus 6. And this will leave me with a half plus 6. So it's 6.5 basically. I can write it in a normal fraction form by saying it's going to be 13/2. Right. So now I have my y for the m. So m I can write now as 1 and 13/2. Right? And then for n, I need to get n, I need to substitute, because I have the y coordinate of n, which is 7. Right? So all I'm going to do is I'm going to substitute that y coordinate. So I'm going to say, to calculate the x, I need to substitute the 7. So this is what I'm going to do. I'm going to say 7, substitute in the place of the y. 7 equals 2 to the power of x minus 2 plus 6. I'm going to subtract 6 on both sides. I'll get 1 equals 2 to the power of x minus 2. Now this minus 2 I can write as 1/4, right? So I can multiply with a 4 on both sides. Then I'll end up with 4 equals 2 to the power of x. Maybe just if I can write out this step, what I did here was I said, just to insert this step, I basically did this. I wrote it in its original format. And then I just multiply by 4 on both sides, like this. And then I get to this part. Now I can write it as 2 to the power of 2 equals 2 to the power of x. And now my bases are the same. So thus, since my bases are the same on both sides, it's easy to see that x will be equal to 2. So my n coordinate is then 2 and 7. So to get the gradient of m and n, we said we're going to use the y coordinate of m, which was the 13/2 we calculated. So that's going to be 13/2 minus the y of n, which is 7, divided by the x coordinates of the two functions. So the m is 1 minus, then we have the x here is 2. So basically 1 minus 2 is just minus 1. So we'll end up with a 13/2 minus 7, okay, divided by minus 1. But if we divide by minus, okay, then dividing this by minus, this basically will happen. I can multiply with a negative top and bottom, to keep the function in balance. And then I'll end up with this 7 minus 13/2 divided by then just a 1. I basically multiplied by a minus, I multiplied the denominator by a minus. So I multiplied this by -1, and then I did it at the top as well to keep the function the same. And so I end up with, if I calculate this, I'll get, it's going to be 1 over 2. So it's a half. So the average gradient, that's 7 minus 13. Just to insert this step, what did I do? I made the denominators the same by multiplying 7 top and bottom with 2. I get 14 over 2 minus 13 over 2. And then that gives me just 14 minus 13 is 1. So I end up with a half, which I got, yeah. And my denominator is 1. So it's basically a half of a 1, which translates to a half. And that's my average gradient for for the M&M points or coordinates. Right, and that's it. I hope that helps. Yeah, and please let me know if you have any questions. Bye-bye.